So this one says, example 7, determine the derivative of f of x equals x to the 1/3, which is the cube root of x, at x equals 0 if it exists. Again, here we're going to use the alternate form. And the alternate form of the definition here was the limit as x approaches c of f of x minus f of c all over x minus c. Okay, and I want you to realize that f of 0, because that's where they're telling us to evaluate it at, would be 0 to the 1/3, the cube root of 0, which is just 0. So that's what we're going to be plugging in for f of c. So in this case, it's the limit as x approaches 0, that x value that we wanted, f of x, which is x to the 1/3, minus f of c, which was 0, right, all over x minus c, which is also 0 in this case. So this is the limit as x approaches 0 of x to the 1/3 all over x, which would be the limit as x approaches 0 of, well, let's do our subtraction here, right? So if you do 1/3 minus 1, that would be x to the negative 2/3, or that would be, if we write that properly, we would throw it into the denominator, right? So this would be 1 over, well, I don't care if you put it back into radical form or not, but 2/3 in exponential form means we have to square it and then we have to cube root it, okay? But when you look at this, what's happening as x approaches 0, as x approaches 0, this denominator approaches 0. And because this denominator approaches 0, it's 1 over a smaller and smaller and smaller number. You could use a table if you wanted on this one. But because the denominator is getting closer to 0, the whole entire fraction gets bigger and bigger and bigger, so that would approach infinity. And I do want you to notice as you get closer to 0, it's positive, so this is going to positive infinity. All these numbers are positive in this sense, okay? So here we have an answer of infinity. And so if it has an answer infinity, that means it's a vertical tangent. And that tells us that the derivative doesn't exist. The derivative does not exist. Anytime you have an answer of infinity, you have a vertical tangent and your derivative doesn't exist. And again, I'm a nice visual person. I like seeing what the heck just happened. So what does the cube root look like? The cube root looks like a graph, something like this right here. And so what we're talking about is at this point 0, if you looked at the tangent line, you would actually have a vertical line. Well, the slope of a vertical line is infinity. It's undefined, right? It's not an actual number. So whenever you have a vertical tangent line, your derivative does not exist. So Theorem 3.1, something we discussed earlier again, says differentiability implies continuity. Says if f is differentiable at x equals c, then f is continuous. It says this relationship between continuity and differentiability is summarized below. If a function is differentiable at x equals c, then it is continuous at x equals c. So differentiability implies continuity. But it is possible for a function to be continuous at a point and not differentiable at that point. So continuity does not imply differentiability. It doesn't go both ways. It's not an if and only if. And these last two examples are perfect examples where they were continuous. The function exists, the limit exists, and they're the same thing. Okay? The function exists, the limit exists, and they're the same thing, so it's continuous at the point. However, the derivative didn't exist at that point. Okay? So you can be continuous but not differentiable. If you are differentiable, you're definitely continuous.